Hello students, welcome to second lecture of chemical bondings and molecular structure. In previous lecture we discussed about some points about Coastal-Lewis approach, and now let us discuss about our next point, Lewis symbols. So as mentioned in previous point, we will assume that we have a positively charged kernel in molecule or atom and valence electrons surrounded by them, and valence electrons are placed at the corner of a cube. So we know that we have total 8 corners of cube. So that means we can arrange 8 electrons around the positively charged kernel of an atom. So in the formation of a molecule, only outer shell electrons takes part in chemical combinations and they are known as valence electrons. The inner shell electrons are well protected and are gradually not involved in the combination process. That means they are inert and they won't participate in bond formation. So only you have to concentrate is on outermost electrons or valence electrons. So G.N. Lewis, an American chemist, introduced simple notation to represent valence electron in an atom. And these notations are known as Lewis symbols. For example, Lewis symbols for the element of second period are as under. So note here we have lithium to neon, and we know that they contains more electron than as mentioned here or as shown in this representation. We know that lithium contains total 3 electron because its electronic configuration has 1s2, 2s1, and the atomic number of lithium is 3. So that means it must contains 3 electron, but out of 3 only 1 electron is valence electron because it is present in outermost orbital, and remaining 2 electrons are present in inner orbital because 1s2 2s1 is the electronic configuration of lithium. So it contains 2 electrons in 1s orbital and 1 electron in 2s orbital. Similarly, as we move from lithium to neon, number of electrons in second orbit will increase and all of the electrons present in first orbit will remain inert, or they will behave as inner orbital electrons, so they won't participate in bond formation. So point is, all you have to do is represent the number of electrons present in outermost orbital or valence orbital, and this is Lewis symbols. So as you can see, we have 4 electrons in carbon as a valence electron, so 4 dots around the carbon. We have 7 electrons around the fluorine, then that means 7 dots around the fluorine, and all of the 8 electrons are fully filled in neon, so 8 dots around the neon. So what is the significance of this symbol? So the dots represents the number of electrons around the kernel. That means in case of neon, as we know, we have total 10 electrons. But let us divide it as mentioned earlier. That means positively charged kernel and valence electron. So first of all, what will be the electronic configuration of neon? So it will be 1s2, 2s2, 2p6. So as we know, electrons present in 1s orbitals will be part of a kernel, positively charged kernel, and remaining electrons will be part of valence electron. So from a part of electron we have total 10 protons and 10 neutrons inside the nucleus. Along with these, 2 electrons present in 1s orbital will be the part of kernel. So this is our kernel of neon, which is mentioned here at the center. Okay, so it contains 10 protons, 10 neutrons and 2 electrons, and remaining 8 electrons will be valence electrons. So they are mentioned around the neon. So this is symbolic representation of positively charged kernel as well as valence electrons of neon, and for remaining second period elements as well. This number of valence electrons help to calculate the common or group valence of the element. The group valence of the elements is generally either equal to the number of dots in the Lewis symbols or 8 minus the number of dots or valence electrons. That means As mentioned in these symbols, let us try to figure out what will be the valence of given elements. So for lithium, number of valence electron is 1 and the valency or number of formation of bonds is equal to 1 as well. That means number of electrons and valency both of them are same for lithium. Same for beryllium, it is 2. Same for boron, it is 3. Same for carbon, it is 4. And now situation will be flipped for nitrogen and onwards. Number of valence electrons, they are 5 in case of nitrogen. And what is the valency of nitrogen? It is 3. That means 8 minus number of valence electron, which is 5. That means it will be 3. For oxygen, it will be just like nitrogen, 8 minus 6. That means 2. For fluorine, 8 minus 7. That means 1. And for neon, it will be 8 minus 8. That means 0. Okay, so these are the valencies of given elements. For some elements it is equal to number of valence electrons, and for some elements it is equal to 8 minus number of valence electrons. So how can we decide for which elements we can use number of electrons is equal to number of valency, and for some 8 minus number of electron or valence electrons is equal to valency. For that you have to do is observe the number of electrons or 8 minus valence electrons. So lower value will be the valency. So as you can see, for lithium, let us try. Number of valence electron is 1 and 8 minus number of valence electrons is equal to 7. So lower number will be the valency. So here our valency for lithium, it will be 1. In case of boron, number of valence electron, it is 3 and 8 minus 3 is equal to 5. So lower number represents the valency. That means it will be 3. In case of oxygen, it will be number of electrons, it is equal to C, and 8 minus 6 is equal to 2. So that means in this case valency is equal to 2. In case of neon, number of valence electron is 8 and 8 minus 8 is equal to 0. So we have 0 valency for neon. If you have common or same number like carbon, as we can see, we have 4 valence electron and 8 minus 4 is equal to 4 as well. So both of them shows similar thing. So you can choose either of them. So valency of carbon will be 4. That means you have to concentrate on lower number. So lower number represents the valency of given element. Next is Kossel in relation to chemical bonding drew the attention to the following facts. First is, in the periodic table, the highly electronegative halogens and highly electropositive alkali metals are separated by noble gases. So that means between them we have noble gases in each cases. The formation of negative ion from a halogen atom and positive ion from an alkali metal atom is associated with the gain and loss of electron by the respective atom. That means if you have a highly electropositive element like metals and highly electronegative elements like halogens, when these two atoms combines with each other, highly positive element will lose the electron and highly negative element will gain the electron. That means lose and gain of electron. So that means, as for example, if you combine sodium with chlorine, then sodium loses electron and chlorine gains it. Okay, so that's why by lose and gain electron they combines with each other. The negative and positive ions thus formed attain stable noble gas electronic configurations. The noble gases, with the exception of helium which has duplet of electron, have particularly stable outer shell electronic configuration of 8 electrons, that is ns2 np6. Let us use same example as before. So sodium and chlorine. So electronic configuration of sodium is 1s2, 2s2, 2p6, 3s1. And for chlorine it will be 1s2 2s2 2p6 3s1 3p 3s2 3p5, and their Lewis symbols are mentioned next to them. So as we can see, we have only one electron as a valence electron in sodium, so one dot around the symbol of sodium, and we have total 5 plus 2 7 electrons around the chlorine, so total 7 dots around the symbol of chlorine. So as we can see, number of valence electron in case of sodium is equal to 1. That means it will be its valency. And number of chlorines, valency of chlorine will be 8 minus 7, because it has 7 valence electrons. So it will be 1 as well. So in this case, they will try to gain noble gas like electronic configuration by lose and gain of electrons. So sodium loses electron and it will give its electron to the chlorine. So number of electrons in 3s orbital of sodium, it will be 0, and number of electrons in the case of chlorine, now it will be 6. So that means now we have to change the Lewis symbols for both of them as well. Now 3s orbital contains 0 electrons in sodium, so we have to cancel it out. So new outermost orbital for sodium, it will be second orbital. So as we can see, it contains 8 electrons, so symbol of sodium will be 8 dots around the sodium. And for chlorine, now it also contains 8 electrons, so new symbol for chlorine, it will be 8 dots around the chlorine as well. But in case of sodium, now it is positive ion, and chlorine, it will be negative ion. Next, negative and positive ions are stabilized by electrostatic attraction. For example, the formation of NaCl from the sodium and chlorine, according to the above scheme, can be explained as we discussed, Na loses electron and it becomes Ne, neon-like electronic configuration, and chlorine gains electron and it gains octet like argon, total 18 electrons. Now positive sodium and negative chloride will combine with each other to form NaCl molecule. Similarly, formation of CaF2 may be shown as, now calcium, as we know, it contains 2 extra electrons than argon. So it will lose 2 electrons and it will form positive ion and argon like electronic configuration, because its number is 20. So it contains 20 electrons. And for fluorine, it contains total 7 electrons in valence electron. So it will gain 1 electron from calcium. Calcium released 2 electrons, so 1F will accept 1 electron, and to accept second electron we need second fluorine. So both of them will gain 1 electrons from the calcium, and octets of each fluorine will be completed and it will become like neon. So then Ca2 plus will attract 2 fluorine negative ions, F minus, and it will form CaF2 molecule. The bond formed as a result of electrostatic attraction between the positive and negative ion. Now electrostatic, that means because of opposite charges, attraction because of opposite charges. So positive and negative ions was termed as electrovalent bond. The electrovalence is thus equal to the number of unit charges on the ion. Thus calcium is assigned a positive electrovalence of 2, while the chlorine a negative electrovalence of 1. Causal's postulates provide the basis of the modern concept regarding ion formation by the electron transfer and formation of ionic crystalline compounds. His view have been proved to be the great value in the understanding and the systemization of the ionic compounds. At the same time, he did recognize the fact that the large number of compounds did not fit into this concept. So that means he only explained bond formation based on ionic bond formation between the ions, but we know that some molecules are not ionic, like methane, and almost most of them are not ionic. We have very large number of non-ionic molecules which forms covalent bonds or coordinate covalent bonds, and we have some large number of ionic bonds as well, but if we compare them with each other, then number of ionic compounds are less than number of covalent compounds. So that means we need more theories which can explain the covalent bondings as well. So our next point is octet rule. So Cosell and Lewis in 1916 developed an important theory of a chemical combination between the atoms known as electronic theory of chemical bonding. According to this, atoms can combine either by transfer of valence electron from one atom to other, gaining or losing, just like as mentioned in case of sodium and chlorines, or by sharing of valence electron in order to have octet in their valence shells. This is known as octet rule. So either way, all the atoms are trying to complete their octets. That means either by losing or gaining electrons or by sharing it. So now let us move on covalent bonds. Langmuir in 1919 refined the Lewis postulates by abandoning the idea of the stationary cubical arrangement of the octet. As mentioned initially, all the valence electrons are present at the corner of cube around the kernel. So by introducing the term covalent bond, Lewis-Langmuir theory can be understood by considering the combination formation of a chlorine molecule Cl2. Cl atom with the electronic configuration neon core 3s2 3p5 is one electron short of argon configuration. As we know, it contains 17 electrons, and to gain noble gas like electronic configuration, it is close to argon, so it only needs one electron for that. The formation of Cl2 molecule can be understood in terms of the sharing of pair of electrons between the two chlorine atoms. Each chlorine atom contributes one electron to the shared pair. That means both of the chlorine will have one pair common of electron, and in that pair both of them are contributing one electron. As we can see here, we have Lewis symbol representation of chlorine atoms, and cloud of electron is mentioned around the each chlorine. So both of them contains one single electron, as we can see here, and both of them lacks one electron to gain noble gas like configuration. So they will share single electrons present in them like this, and common electrons are now part of both of the chlorines. So we have one electron pair common between the two chlorines. It is just like a business partnership. When two or more persons don't have enough money to run a business, then they will partner up with each other to run a common business. So same thing is happening here. Two chlorines do not have enough electrons to fulfill their octets, so they will share their electrons, and now both of them have enough electron to complete their octets. So this type of Lewis dot structure can be represented for other elements as well, or other molecules as well, in which the combining atoms may be identical or different. The important conditions being that each bond is formed as a result of sharing of an electron pair between the atoms. Each combining atoms contributes at least one electron to the shared pair. The combining atom attains outer shell noble gas configurations as a result of the sharing of electron. That means if they do not gain noble gas like electronic configuration, then there is no meaning of sharing the electrons with each other. Thus, in water and carbon tetrachloride molecules, formation of covalent bonds can be represented as we can see here, we have total 6 electrons in oxygen and one electron in hydrogen in case of water molecule. So that means hydrogen will try to gain noble gas like configuration near to it. That means helium. So it needs one electron. And oxygen contains total 6 electrons as well as electrons, so it requires 2 electrons to gain noble gas electronic configuration. So oxygen will share one electrons with each hydrogen, and same will do the hydrogen. So as we can see, hydrogen gains total 2 electrons around it, and oxygen gains total 8 electrons around it. So both of them, or all of these three, has complete octet. Here exception will be for hydrogen and helium, because helium is also a noble gas, and its outermost electronic configuration is fully filled and stable, although it is not 8 electrons, but still it is exception, and helium like electronic configuration are also stable. In case of carbon tetrachloride, as we can see, carbon has total 4 electrons in its valence shell. So it requires 4 electrons to complete its octet. So it will share 4 electrons with 4 different atoms. As we can see, in this case, 4 different atoms are chlorines, and chlorines requires 1 electron to complete their octets. So they will share 1 electron with carbon. Each chlorine will share 1 electron with carbon. So all of the 8 chlorines has all of the 4 chlorines has 8 electrons around it now, and each electron is shared by carbon. So carbon also gains 8 electrons around it. So all of them has fulfilled their requirements. Thus, when two atoms share one electron pair, they are said to be joined by single covalent bond. In many compounds, we have multiple bonds between the atoms. The formation of multiple bonds envisages sharing of more than one electron pair between two atoms. If two atoms share two electron pairs of electrons, the covalent bond between them is called double bond, and same is with three electrons. If they share three electron pairs between them, then it will be called triple bond. For example, in the carbon dioxide molecule, we have two double bonds between the carbon and oxygen atoms. Similarly, in ethene molecule, the two carbon atoms are joined by a double bond. So as we can see, in case of oxygen, it requires 2 extra electrons. In case of carbon, it requires 4 extra electrons. So oxygen will share 2 electrons with 2 electron of carbon. So they have total 2 pairs of electron between them. And same with carbon. Carbon requires 4 electrons. So that means it will share 2 electrons with each oxygen. So carbon has total 4 pairs of electron around it, and octets are complete. So they have double bonds between them as shown in adjacent image. Now note here, in this image, as we can see, electron pair not shared between the elements are still mentioned on each oxygen here. Okay, so that means these dots only belongs to oxygens, and if electron pairs are shared between the atoms, then dots of those shared electron pair will be represented as straight line, as we can see here. So that means this straight line actually represents shared electrons between the carbon and oxygen, and this pair belongs to both of them. One electron belongs to each of them. And the same type of structure is mentioned for ethene molecule as well, C2H4. As mentioned earlier, hydrogen requires 1 electron and carbon requires 4 electron to complete octet. So hydrogen will share 1 electron with 1 electron of carbon, and carbon will share 1 electron with 2 different hydrogen and 2 electron with second carbon. And that's how it completes its 8 electron requirement, and second carbon follows the same. Now notice here, none of them contains separate electron pairs belong to them. All of these electron pairs are shared electron pairs. That's why in adjacent structure, no dots are mentioned around any of the elements mentioned here, because none of them contains unused electron pairs. Now when combining, the atom shares 3 electron pair, as in the case of 2 nitrogen atoms in N2 molecule and the 2 carbon atoms in the ethene molecule, a triple bond is formed. So same as before, as mentioned earlier, nitrogen contains total 5 electrons around it as a valence electron, so it requires 3 electrons. So it will share 3 electrons with second nitrogen, and we have total 3 shared pair between these two nitrogen, and 1 pair belongs to each nitrogen. That's why in this representation, both of them still contains unused electron pair which belongs to them, and 3 bonds represents 3 pair of electrons shared between them. Similarly, representation of ethyne molecule represents the same. Carbon requires total 4 extra electrons, so it will share 1 electron with hydrogen and 3 electron with second carbon. As a result, it has total 8 electrons around it, and same for second carbon. And as a result, none of them contains unused electron pair, so no dots on them. So till this point, if you find any difficulties in postulates or any explanation,
feel free to ask, and we will continue with next lecture.